Tenemos que cambiar para inglés, ¿eh? ¿Está bien?
Yes, yes. Change.
Sí, sí. Change.
Change the. Change
So
the.
let me see. I see the name of João Rosa, Kent Yagi, and also Martin Nava, Nan Jiang. Please, can you activate the sound, please?
Yes.
Yes. Okay.
Yes. Okay.
Okay, and the camera also, please, just to.
Hello.
Can you do that? Yes.
This is Kent.
Oh, Kent, how
Yes.
are you? Fine.
Hello.
Well,
Yes. Hello. Yes. Good. Very
Oh,
good.
hello.
Yes.
Hello.
Happy to happy to know to see you. So, according to our list of presentations, we have, well, the title of the section, as you know, is Compact Stars as Laboratories for Testing Strong Gravity. So we have to start with João Rosa. Yeah, João.
Yes.
João. Okay, you are here. Then we have the next one is Aurora. Oh, Aurora is the next one. Okay.
Ah, yes?
The second, yes, the second one, and then we have Martin Javier Nava Calejas. Are you there, Martin?
Here.
Yes.
I'm here.
Oh, okay, good. In the work with my friend Danny Page, yes? Okay, good. And then we
Yes.
have Leonardo Mastro Totaro di Napoli. Ah,
Okay.
Leonardo, ok. Di Italy. Io sono anche italiano, Leonardo. Italiano brasiliano, anche italiano. Io sono. Si può parlare in italiano anche, ok? Kenti Agi, are you there?
yeah, I'm
Kent.
here.
Oh, okay, good. Good to see you.
Yeah, good to see
Then
you
we
too.
have, okay, good. Then we have the work of Caesar and Beno. Beno will be the present, the collaboration and.
Yes,
Okay.
I'm here.
Fantastic. And then Manuel Malheiro, he's not here already. Rodrigo Tenorio, are you there? Rodrigo? No. Rodrigo is not there. And then we have Nan Jiang. Oh, fantastic. Good. And then we have the following one is Mikhail Stepanishka. Or I'm sorry if I. Are you there, Michael? Michael. Okay. So I think we can start to organize the presentations and share a screen with João Rosa. Okay, João? Just to be on the safe side. That's okay?
Yes, let's try.
Okay, let's try. I have
Please let me know
to.
if it is working.
Yes. I think I have to make you to give you a new status, okay? Then you give me back the status, okay?
I am sharing already.
I think it's out of.
Ah, you are sharing. Ah, sorry. Good.
Okay, perfect.
Okay.
Okay, perfect.
Oh, that's fantastic. Okay. Oh, you are sharing. Okay. I don't see your screen.
I stopped already. Let me try again.
Okay, please try again. Because fantastic. So just keep this way, okay?
Okay.
And then in a few minutes we start with your presentation.
All right.
Okay? Well, if everybody agrees, we can start now. Okay? Because we
Yes.
are recording, and if someone will come a little bit later, he can, in other moment, access the record and so on if he wants. Yes?
Yes. Yes.
Everybody agrees? We can start?
Yes. For me, yes.
Yes?
Sounds
Yes?
good.
Okay, so you can start, Joan. You have 15 minutes, and we leave questionings for the end of the section. That's okay?
Okay, sure.
It's okay.
Okay, 15 minutes, please.
Thank you very much.
Please.
So my name is João Luís Rosa. I am a postdoctoral researcher at the University of Tartu in Estonia. And today I bring you a work I have done with my student Pedro Pissarra that was published last year here is the reference. So I want to start by stating that today we have a lot of observations that seem to indicate that objects that behave like black holes exist. And as examples, let's consider, for example, the movement of stars orbiting around the center of our own galaxy. And also recently, we have seen the first shadow of a black hole in the center of the galaxy M87. So observations indicate that black holes exist. But black holes are not only sunshine and rainbows. Black holes have problems. They have horizons, they have singularities, they have this information loss paradox. So it would be very important if one could develop a model for an alternative compact object that somehow reproduces the same observations that we have today, but does not feature the same problems of horizons and singularities. And we want these problems to be solved as simple as possible. So let us consider GR for this approach. Many different alternative compact objects were proposed. One such object is a so-called Schwarzschild star. The Schwarzschild star is a star made of a perfect fluid with a constant density. The exterior of this star is represented by the Schwarzschild metric, as it is represented here, where the mass m is the total mass of the star. And the interior solution where the perfect fluid is described by another metric, a little more complicated, that is known as the interior Schwarzschild metric. Now, the problem with this kind of objects is that if you compute the central pressure of this object, you obtain something like this. And if you compute the central pressure of the object for different radii of the object, you will see that the central pressure diverges when the radius of the object is smaller than 9/4 of m. This is called the Buchdahl limit. Now, the Buchdahl limit was obtained for objects that are spherically symmetric. They are isotropic, and they have non-increasing density. There are many ways of avoiding the Buchdahl limit. One such way is, for example, to consider anisotropic objects. In this talk, I'm going to propose other models for compact objects that do not have to satisfy the Buchdahl limit because they violate one of the assumptions, which is non-increasing density. So to obtain solutions like the Schwarzschild star, we have to use the junction conditions of the theory. The junction conditions are a set of conditions two spacetimes must satisfy in order to be glued, let's say, at a given hypersurface of the whole spacetime. So let me introduce you some notation. Sigma is going to be the hypersurface dividing the interior and the exterior of our object. V minus and V plus are the interior and exterior spacetimes that are described by metrics written in coordinates xa minus and xa plus. Y alpha is going to be the set of coordinates in the hypersurface, and NA is going to be the normal vector to this hypersurface. Now, the induced metric and the extrinsic curvature, so the induced metric at the hypersurface and the extrinsic curvature can be defined in these two ways, where these vectors E, A alpha, E, B, beta, etc., they are the projection vectors. So if you take some quantity in the whole spacetime, let's say, for example, the metric with two indices, and you project this metric with two of these vectors, you obtain the metric at the hypersurface. And the same thing for the extrinsic curvature, which is basically the covariant derivative of this normal vector projected again onto the hypersurface. When you obtain the Schwarzschild star is called a smooth matching between the interior and the exterior spacetime. And this is because we obtain continuity of the induced metric and the extrinsic curvature. In here, This parenthesis, this square parenthesis, then denotes the jump of the quantity across the upper surface. So if the jump of the quantity is equal to 0, this means that the quantity does not change from the interior to the exterior surface, or in other words, this quantity is continuous. And for the Schwarzschild star, this is what happens. At the upper surface, the induced metric and the extrinsic curvature are continuous. The first of these equations is mandatory, but the second one does not have to be, is not mandatory. So one can also try to find solutions for compact objects for which the extrinsic curvature is not continuous. And if you do so, something called a thin shell will arise at the separation. And this thin shell, the stress energy tensor of this thin shell is given in terms of the jumps of the extrinsic curvature and its trace. And if you raise one of the indices, you can actually compute the density and the pressure of this thin shell. So this is what you're going to do. We're going to use these junction conditions to build two different models for compact stars based on this approach. The first of the models we are going to choose is take a Schwarzschild star with some radius greater than the Book-Dahl radius and collapse the exterior layers of this star into a thin shell. In the end, in principle, the radius of this shell can be smaller than the Book-Dahl radius. For the second model, we are going to take some star which has a radius smaller than the Book-Dahl radius. This means that inside this star there is a singularity somewhere, and then we open a vacuum bubble inside this star to remove the singularity. So in the end, you can again obtain a solution for a compact object with a radius smaller than the Book-Dahl radius, but without having singularities nor event horizons. So let's see the results. This is the result for the first model. In here, I plot the surface energy density of the thin shell and the surface tension of the thin shell as a function of the radius at which we perform this matching. And as you can see, if the radius that we perform the matching is equal to the radius of the star, these are the different radius of the star, the thin shell disappears. So the density of the thin shell goes to 0, the pressure of the thin shell goes to 0, and the thin shell disappears. But if you make the matching, if you collapse the star, the exterior layers of the star at some radii, you will see that there is this thin shell appearing. So the density and the pressure are different from 0. So there is actually some kind of matter separating the two spacetimes, like basically pretty much like the surface of the Earth, let's say. Now, to verify if these models are physically relevant or not, the first thing we have to do is to check if they satisfy the energy conditions. So in here, I plot the density plus the pressure, which is the weak energy condition, and the density plus twice the pressure, which is the strong energy condition. And as you can see, the result is positive everywhere. So in here, in the y-axis, we have the initial radius of the star. In the horizontal axis, we have the radius of the shell. And as you can see, this combination, sigma plus pt and sigma plus 2pt, they are positive everywhere, which means that this model satisfies the weak and the strong energy condition. Let's look into model number 2. For model number 2, the situation is the opposite. We are opening a bubble inside the star. So we are expecting the density to disappear when the radius of the shell is 0, which is exactly what happens here. And in here, we have the same thing for the pressure. When the pressure only vanishes if the radius of the shell is equal to 0, except in this particular case, which is the Book-Dahl radius, that we already know the pressure diverges at the origin. Now, if we compute again the energy conditions for this second model, there is indeed a region where these energy conditions are violated. Again, we have sigma plus pt and sigma plus 2pt. But the thing is, this white line here, this white line is the region where the singularity appears. So for example, if you consider an object with a radius exactly equal to the Book-Dahl radius, which is exactly here, you will see that for any radius below, we will have a singularity. So this is exactly where the singularity is. So if you open a vacuum bubble big enough to remove the singularity, you automatically fall in the region where the junction conditions are satisfied. So once again, if you remove the singularity, junction conditions are satisfied, and this is exactly what our model predicts. We want to remove the singularity, and in this case, the energy conditions are satisfied. Now, the energy conditions are not the only thing that must be satisfied, let's say, to guarantee that the model is physically relevant. Besides that, the model must be stable against perturbations. So to analyze the perturbations of on the spacetimes, what we will do is to consider radial perturbations of the thin shell. We consider the thin shell. This is a static model. Each of the two models I presented before, they are static models. And now we take this model and we slightly perturb the radius of the thin shell. Now, what's happening here? If the model is stable, when we perturb the radius of the thin shell, it will oscillate a little bit, but eventually return to the equilibrium state. And if the object is unstable, then if you make a small perturbation in the radius, the object either expands forever or contracts forever. So this is not a suitable object this is not a physically relevant object, let's say. To study the stability of these objects, we will have to find then the equation of motion for the thin shell, which can be obtained from the stress energy tensor of the thin shell. We then, since we are interested in small perturbations in the radius, what we have to do is simply to expand this potential to, let's say, to second order in the perturbation, and we ignore all the terms of higher order. Notice that in the first order, the potential is a constant because we are in an equilibrium position. And furthermore, the derivative of the potential is also zero because we are, again, at an equilibrium position. So the first term that matters is the second order term. So the second derivative of the potential with respect to the radius. Now, this second derivative of the potential, it will depend on the density of the thin shell, the pressure of the thin shell, the derivatives of these two quantities with respect to the radius of the thin shell, etc. To find these quantities, we will have to take, for example, the conservation of the stress energy tensor. And from this conservation of the stress energy tensor, we will be able to write the derivatives of the density of the thin shell in terms of the density itself plus the pressure, plus one extra term, that is the discontinuity in the momentum flux. So because the shell is not in vacuum, the shell is vacuum outside, but in the inside, the shell has some kind of fluid. When the shell oscillates, there is going to be some matter passing from the fluid to the thin shell and vice versa. So there is this extra term that does not appear when we are considering the thin shell formalism in vacuum. So if you consider this term, and if you solve these equations and find the second derivative of the potential, the stability is very simple. If the potential is, the second derivative of the potential is positive, the solution is stable. And if it is negative, the solution is unstable, just like a particle in a one-dimensional potential. So let's check the results. In here, I plot the value of the second derivative of the potential as a function of the radius, the initial radius of the star in the y-axis, and the radius of the shell in the horizontal axis. And as you can see, this, by the way, this red line here denotes the Bookdahl radius. And as you can see, there are solutions, for example, in this region here in green, a very small region here in green. I hope you can see it. In this region, we have a solution that is stable, that satisfies the junction conditions, and that has a compactness arbitrarily close to that of a black hole. So it is a black hole mimicker, let's say. Another important thing we have to consider, or at least it's not super important, but it is an important conclusion to take, is to check what happens to the dominant energy condition. Because in the 90s, Eric Poisson has shown that the dominant energy condition and the stability regimes, they are closely connected. If the dominant energy condition in a black hole spacetime with a thin shell is violated, then the solution is unstable. In here, however, this is different. There is indeed a region where the solution is stable, but the dominant energy condition is violated. So indeed, the conclusion that Eric Poisson took in black hole spacetimes like almost 30 years ago, it's not valid when you consider compact objects with fluids. So this is a very important conclusion. But nevertheless, even if you want your object to satisfy the dominant energy condition, you can still have objects with radii up to 2.1 m, so still smaller than the Bookdahl radius. For the second model, this is the result. So indeed, once again, we have a region here where the energy conditions are satisfied, but the solution is unstable. But nevertheless, we still have a small region here where the solution is stable and the energy conditions are satisfied. And as you can see, this region moves all the way down to R equals to M. So again, there is the possibility of building a stable solution that satisfies the energy conditions, the strong and the weak, and that has a compactness arbitrarily close to that of a black hole. So again, this is exactly what we are looking for. Finally, you can also look at the dominant energy condition. And again, the same thing verifies. So in here, you will have an object that violates the dominant energy condition, even though it is stable and satisfies the weak and the strong energy condition. But if you want the dominant energy condition to be satisfied, you can still find objects in this model all the way down to 2.1 M. So again, still smaller than the Bookdahl radius. So to conclude, my conclusions I have already stated throughout the talk. So let me just point out what's left to do here, because as you can see, and as you probably will argue, these models are unrealistic. They are just, let's say, toy models to test a new possibility to find compact objects, in this case, by using the thin shell formalism. But there are more things we can do, not only to test these objects, but to create more realistic objects. And one of those things is to compute the quasi-normal frequencies of these objects. These frequencies could be then observed in gravitational waves, and it can infer if these objects are good or not. And besides that, since these objects do not have event horizons, they will have gravitational echoes and tidal effects also detectable in the gravitational wave signal. So this is a good test for these objects. And finally, just to finalize, it would be very important if we know that most of the objects in the universe are rotating, these objects are not. So looking for a generalization to rotating models using this formalism would also be a very good thing to do. Thank you very much, and I'm here to answer.
Okay, thank you very much, Ron. So let's immediately go to Aurora Perez Martinez, please. Okay, very good. Aurora? Aurora, ¿me escuchas? Aurora. Alô? Aurora? Aurora?
Okay.
Tá. We have to share
Yes.
screen, yes?
Yes,
Okay.
please. 1 minute, please.
Okay. No, that's okay. Take your time. Just I am, anxious as any organizer. Typical of organizers.
I try to share, but I can.
I'm sorry.
Okay, let me see this one.
Yes.
No, but can you see?
No.
Okay.
Should I change your status? Maybe.
Huh?
Should I change your status? Maybe.
Yes. Maybe.
Could be. Let me see. Okay. Now
Okay.
you are a co-roast. But please give me back this, yeah?
Okay. Close the windows, and I try.
Okay.
I try to share. Hello. 1 minute.
Yes.
I think you only have to click the share screen button below. And then you choose
I don't know.
window.
In the screen, below in the screen, you have to click share screen. Share screen. Compartir. Para compartir. Tá perfecto. Tá perfecto. Muy bien. Hecho. Ahora está hecho.
Let me see. It's okay? You can see.
It's okay.
Yes.
It's okay. Go on.
Okay.
Go on.
Okay. Well, good afternoon. It is a pleasure for me to talk here in this conference, and my talk is entitled Vacuum Properties and Astrophysical Implications, and is a work in collaboration with Maria Ángeles Pérez Garcia, who works in Salamanca University. I am here too. This work also is in collaboration with Elizabeth Rodriguez Kerr, who is from Cuba, Instituto de Cibernética, Matemática y Física, and also with Adrián William Romero, who is my student, undergraduate student, but his thesis is about this topic. So the outline that I follow is a briefly motivation about the topics, and then I will show you perturbative calculation, QED, in presence of magnetic field, and the different limits, weak field limits, strong magnetic field limits, and also I show you the index, refraction index, phase velocity in the two approximations, and I will try to reproduce, for first preliminary, try to reproduce the observational results and to show if it is a signal or not of this reference. Then I will show you some conclusions about the work. So in spite of QED has a lot of experiment tests, it predicts brief references and it remains without experimental tests in lab. And the reasons about that are that this effect is small for maximum values of the magnetic field obtained in lab. In PV-LAS experiment, this magnetic field is around 1 Tesla, 10 Tesla, something like that, and the effect is very slow. But maybe there are another possibility that is that new physics are behind these results. So there are a lot of experiments proposed trying to verify QED or to look for new physics. So this experiment goes to improve magnets or to use pulsating lasers to simulate the magnetic field. So there are another way to think to check the reference, and this is to look for a universe, to look for magnetars, neutron stars, or pulsars, because they have a strong magnetic field, you know, around 10 to 13 Gauss or more, and we can check this property using the astrophysical data. So there are a first announcement in 2017 suggested that it could be checked the reference using this pulsar Earth-X G 856.5 and the other numbers, no? This is a source, and the authors claim that they get some evidence about the reference. But I want to explain you very fast what is a vacuum reference. So if we have a medium, you know that the light can to experiment change of velocity because through the medium, no? And the dispersion relation is not the line cone. Well, in the vacuum, in the presence of magnetic field, we have a similar effect. This vacuum is not really, is not a pure vacuum because we have pairs, electron-positron pairs that interact with the magnetic field. So depending on the direction of propagation of the light, we can get a different phase velocity or not. So in the case of we have the reference, which is this spread, photons time, a photon that travel this medium, this vacuum, arrive to the detector a high energetic photon later than low energetic photon. So this is the way to measurement the reference through pulsars. In this picture, we plot the time delay as a function of the magnetic field for some pulsar that we have the values, the magnetic field and also the time delay. And you can see how they describe a line here, which is linear with the magnetic field. So we start from photon self-energy eigenvalues of this self-energy. We solve this equation for photons, and we diagonalize the self-energy of photons and resolve the dispersion equations given by this. Depending on the angle that form the magnetic field with the vector wave of photons, we have that appears two modes where they have different phase velocity, on one mode which is non-physical, that is this kappa 1. So if the photon is parallel to the magnetic field, the light goes with the same velocity, speed of light, so they don't feel the magnetic field, so they don't interact. The magnetic field that are important in this problem is given by the critical field that is 4.41 10 to 13 Gauss. This is the critical Schwinger field, and you know that we take the limit below or above the magnetic field. So in astrophysics, we need to consider a strong magnetic field because we have fields higher than this value, but in lab, where we try to look for evidence about birefringence in lab, we use the weak magnetic field limit. So this is the eigenvalues here for weak field, here for a strong field. We can see that in first approximation, we have that this weak field gives us a dependency equal to B2 square, and a strong magnetic field goes linearly with the magnetic field, and there are some, this mode, the 3 mode, that is almost constant. So we always go consider a frequency below to the thresholds of creation pairs. So we have radio wave up to soft gamma rays in order to check the behavior. So the refraction index in this limiting width limit give us these results, also proportional to B2 square and linear with the magnetic field, and also this mode which is independently of the magnetic field. So the comparison of this refraction index with the magnetic field and also the velocity with the magnetic field, you can see that if we consider that we have magnetic field in, for values higher than the critical field, we have in a strong field approximation. So if we use weak field approximation, of course, we have underestimate and overestimate the refraction index and the velocity of photons. So we have bad results if we consider not appropriate approximation for the magnetic field. So we try to do a comparison with observations. This pulsar, these sources, is the most closer pulsar to the Earth, and the observational data give us that the fraction of polarization photon is 16.4%, and the angle is 145 degrees. So we try to write our results given in terms of refraction index in order to calculate the angle through the vector Stokes vectors. So we work with these quantities, and we're trying to do a calculation, consider a dipolar magnetic field, a strong field approximation for the refraction index, and we suppose radial trajectory for photons. So consider these values for the magnetic field, the period of the pulsar in this range, and also the radius that is possible to consider that we are in the vacuum is around these quantities, 19 to 41 kilometers. We can do the calculations, and we have very good results. These results are obtaining today, but they are very, very preliminary with this fraction as a function of the frequency. And this is of the same order. But when we try to compare the angle, we have that the angle is lower than the observational angle. So we need to check our calculation. We need to do some other consideration in order to check if we have some mistake or the results we need to see again. So we can see how this fraction of polarization photons is a function of frequency. If the frequency of photon is higher, we obtain a high fraction of polarization photon, and also this fraction depends on the period of the pulsar, and when the period increase, the fractions decrease. So the conclusion is that this is a work in progress. Our theoretical calculations are in agreement with the linear dependency on the delay due to, from the data of observational magnetic field and time delay of pulsars. The behavior of phase velocity birefringence is in agreement with it was expected, and we have an analytical and numerical expression of refraction index and delay, time delay. And the more energetic photons have a bigger polarization degree than the lower ones. Besides, the fraction of polarization has a strong dependency with the period of the neutron star, because this can increase or decrease the polarization, limiting the radii, causing the coupling or decoupling of the propagation mode. So other effects like medium should be considered. We have a preliminary study related to that. For a dipolar magnetic field, the polarization degree is in agreement with experimental data for this pulsar, but these results need a discussion about if the value of PD lower than 40% can be considered as a strong evidence of vacuum birefringence or not. So we don't have a final conclusion related with this pulsar support or not birefringence. So thank you very much. Gracias. Gracias. I finished.
Okay, okay. Thank you very much, Aurora. Thank you, thank you. Okay, so let's start with the next talk. Is Martin Javier Nava Calejas? Yes, Martin.
Here, yes.
Oh, okay. Let me see if I need to make you co-host. Maybe yes, yeah. So I will make you co-host, okay? In order you can share your screen with us, okay? So tell me if everything is going fine with this new status.
Yep, okay.
Preciso de chá para poder acordar aqui.
Pegar uma chocolate junto lá.
Ah, tá.
Eu abri já do lado.
Ah, tá. It's fine? Yes? Hey,
yes,
Martin.
okay.
Okay. Can you share your screen with us?
Okay.
Okay, perfect.
Okay, so
now it's working.
Fine.
Okay, you can start, please.
Sure. Good morning, everyone. I'm going to talk about proving strong field gravity and the structure of ultra-dense matter within the neutron star thermal evolution of these objects. So, a brief outline of my presentation. There are 6 points. first motivation of the research, then I'm going to briefly describe the FR model of gravity. Then I'm going to talk about physics in general, space-time. Then I'm going to 5 to the neutron stars, a brief review on it, and then the main topic, the thermal evolutions. So let's say some words about the context of this research. As we know, there are several approaches or alternatives to general relativity as the gravity theory. The most immediate extension of this is the so-called f of r, which replace the scalar curvature by a function of it. Of course, neutron stars are a perfect scenario for testing differences between this model of gravity as well as any other one. So in particular, thermal evolution is in this context, well, it could be a good example of possible deviations between both theories. So our questions are, can we construct strong field gravity using nuclear killing? And not how much to uncertainty field gravity limiter study of neutron. So briefly, the formula of gravity consists, as I mentioned it, on the replacement by a function of a scalar curvature. We are treating with classical gravity, so we impose a stationary principle over this action. In order here, we arrive to the expression for the field equations. So-called quadratic model is due to the fact that we include a correction to this R. This parameter alpha is the wish train. And of course, now the trace of this expression becomes relevant, but the conservation of energy momentum tensor holds. So for a first approach on thermal evolution, we start with a static and spherically symmetric metric, as well as a per fluid for the matter content. And if we plug the expression into the field equations, we arrive to these expressions for the field equations, which for the structure equations, which we move numerical methods. Regarding alpha, we shall constrain it for being non-negative. In the case 0 returns to GR. As you can see, there are several constraints from at least 3 sources. We are considering that this is a universal function, so in our approach, we are only the first 2, which are clearly great constraints. So for the thermal evolution, let us emphasize that we are studying both densities and total quantities. These are related to an integration measure, as you can see on the screen. This integration measure considers the lambda function of the metric. Also, 2 kinds of quantities that we shall study: the local ones, which are T and L, and at infinity, that means the one that we measure, which are related to a 0, 0 component of the metric. So for a neutron star described in this frame, luminosity and temperature are functions of time and coordinates, but once the structure is derived, the thermal evolution holds. I mean, once we obtain the structure by solving the previous equations, we can insert them in the equations that I'm now going to introduce, and we can study the thermal evolution. So due to the derivation of this equation that I'm going to introduce were done in Lagrangian coordinates, we think that they are fixed in our theory. I mean, they require no further modification. And as you can see, they relate local quantities with global ones, including, of course, emissions. Here we have neutrino emissivity, heating sources, as well as a specific heat and thermal conductivity. In this parameter, we shall include some features such as the equation of state, which there is some uncertainty regarding the core. Nevertheless, we are assuming to at least models the APR, which consists on non-relativistic or relativistic corrections, and the mean field theory. Some of the important processes regarding the neutron emissions. I'm seeing here that there are several issues with sound. Can you hear me now?
I think you have problems with your sound because people, I think for everybody is they are they experience the same issue with your sound. So maybe we could stop your presentation for a while and go to the next one, and then you can return if you can repair your problems with your sound. Yes?
Okay, good.
Yes? Then you can start again, no problem. Do not worry about, okay?
Okay,
But
okay.
okay, but I think we have to move to the next talk, okay? And then please take a look on your system to see if you can repair the problems you have, okay? So
Okay.
I think we have to move to Leonardo Mastrototaro.
Hello to all.
Leonardo, mi senti?
Yes,
Okay,
yes.
good. Yes, okay. Can you share your screen with us,
Okay.
please?
I
Yes?
can share it,
Yes?
but can you see it?
Yeah, okay. Yes, we can see. Perfect. So
Okay.
please, you can start. No problem, okay? Then Martin will be back as soon as he can repair the problems with his sound, okay? So
Okay.
please, Leonardo, you can
Hello to all.
start.
Hello to all. I'm Leonardo Mastrototter. Thanks for this opportunity. And today I will present my works in collaboration with Professor Gaetano Lambiase on the effect of modified theory of gravity on the neutrino pair annihilation energy deposition. So in this slide, I will do a general introduction motivation for the modified gravity theory. Then I will talk about the neutrino energy deposition enhancement and the GRB effect of this. And then I will conclude my presentation. So why we need extended theory of gravity? As we all know, theorists are trying to join gravity with quantum field theory, giving rise to some theory that are like supergravity, quantum gravity, string theory. And so they introduce some modification to GR, and moreover from observation from cosmology and astrophysics, in particular the existence of dark matter and dark energy that should be over the 19% of our universe, so one can think that it's quite unnatural of this. Maybe one can think that modification to general relativity are needed. Modification can be like function of the curvature, adding a field to the picture or adding torsion to the equation. Indeed, this is the general Einstein equation, and the modification can happen in the G mu sector with a new theory like QFT, string, M theory correction, Brine-Wall model, or we can have modification even in the energy momentum tensor T mu with a cosmological constant, scalar field theory, phantom field theory. So we have a lot of correction and expression that can rise from general theory, and so a lot of metrics that can be studied. And the idea of our work is to study the effect of this modified theory to the process of annihilation of a pair of neutrinos into a pair of electrons and positrons. Indeed, this process is relevant because it's relevant for the delay shock explosion in supernova and in neutron star merger, because these electron and positron can annihilate themselves and create some photons that can reheat the shock of the supernova and that can produce also GRB gamma ray burst with in the context on a neutron star merger. So in this slide we will see a general framework to study the annihilation of this neutrino and the energy deposition, and then we will talk about the GRB. So first of all, we start with a genetical metric that is G mu, that is very generical with the possibility that also G03 is different from 0, and we consider the Lagrangian for a circular orbit as written there. This is because before emitting this neutrino, we approximate it to be in a circular orbit around the huge object that we are considering, and this huge object is described by black hole metric. So we start with generalized momentum, with P0 that is linked to the energy and P3 linked to the angular momentum. And from that, we can write the Hamiltonian, like written in the left in the slide, where delta 1 is a constant that is equal to 1 for massive particle, because all the Hamiltonian is divided by the mass of the particle, or 0 for massless particle. From that, the quite relevant quantity that one can obtain is the R dot squared. And in the picture, the next will be relevant also the impact parameter for a massless particle, that is L divided by E, L over E. This is because we consider neutrino in our treatment like massless particle, because with the energy that are emitted, we can approximate it with a massless particle. So, first of all, the first modification that one can have in this theory, so in a modified theory, is a modification in the photosphere. This is because photosphere is the last unstable circular orbit, and as we all know, in a Schwarzschild black hole, it's the radius of the photosphere is equal to 3m. In general modified theory, we start with R dot square equal to 0 because it's a circular orbit, and so imposing this condition, we can have a relation between E squared and the effective potential, and so deriving the effective potential over R and putting it to 0 because it's a maximum for the potential, it's unstable, we can have the quantity, so the expression, the radius of the photosphere. Photosphere is important because neutrinos are emitted from the neutrino sphere, and its radius has to be larger or equal of that of the photosphere. So the radius of the photosphere is the minimum radius at which neutrino can be emitted. In the next, neutrino sphere will be defined as big R, while small r is the error of a local observer. And this is the expression for the energy deposition rate over unit time and unit volume. And it's quite interesting that it depends from many quantities. So the temperature of that is linked to the temperature of photosphere, the neutrinosphere, it depends on L infinity. L infinity is the luminosity, the neutrino luminosity measured on Earth, and it's considered to be equal varying the matrix, and it depends on the angular integration factor written there. To calculate this angular integration factor, we have to consider the tetraeds, and the general tetraeds are written there, and it's a very generic way to written there, and we define theta r as the angular between the trajectory and the tangent velocity. So u1 over u3, where u is the velocity for measured by a local observer. And in this way, it's possible to obtain a relation between the angle theta r and the impact parameter. I write here an example for the cosinus of theta r in the Kerr metric. And if j is equal to 0, it's possible to obtain the classical example of the GR that is written there in the slide. But in general, we obtain so a relation between b, the impact parameter, and f, so a function of the cosinus of theta r. And due to the consideration that b is equal among all the trajectory, we can have that, and that the neutrinos are emitted with theta r equal to 0. We can have a relation for cosinus theta r very formal, like written in the right of the slide. It's very formal, and for each metric, one has to derive this cosinus of theta r to obtain the energy deposition. So in this way, obtaining cosinus of theta r and putting it in the angular integration factor, we can obtain an expression for the energy deposition over unit time and unit volume. And the last step that we do is to integrate this expression to over the volume to obtain the energy deposition rate over unit time. That is that big Q dot written there at the end of the slide. So this is an expression for Q dot with a matrix with G03 equal to 0, we can have also the expression for G03 different from 0, as I said before, but it will be more complex. And the relevant fact is that the energy deposition depends on the factor F that is written there. And the factor F, it's relevant because in the non-relativistic limit, so in the Newtonian limit where m goes to 0 in the G00, f of 0 is equal to 1. So when one wants to compare different metrics with respect to the Newtonian gravity, for example here, GR respect to Newtonian gravity, what one has to calculate is only the factor F. So the factor F will be the factor that we will compare between over the matrix to obtain to see if the modified gravity can increase the energy deposition by the processes of annihilation of neutrinos. So this is a first example in the Gauss-Morley gravity, where we modify the action of GR with a field and with some powers of the curvature. The black hole solution depends on F of R and H of R, but in general depends on a parameter alpha. And switching on this parameter, we see how the blue curve increase respect to GR, that is the green curve. We can see an enhancement so in the energy deposition for these neutrinos, and also more big photosphere radius respect to GR. The same can be observed even here in this example, where the gravity is modified like there. We have also that the solution depends on the parameter omega. We have here that the photosphere radius reduced respect to GR, but we have also an increase, the black curve, of a factor 3, more or less, respect to GR. So we observe that in these two metrics, always an increase, an enhancement respect to the energy deposition of GR. And the last example that I want to bring to us is the quintessence example, where the quintessence is the... sorry, I see some messages.
No problem. Just take our time.
Okay, sorry. So the quintessence can be in the universe, and the quintessence matrix is there in the slides, depend on the parameter C and omega Q. And also for the quintessence, we can have an increase in the right picture there, an increase also of more or less 2 order of magnitude respect to GR. That is a very huge increasement. And why this increase is relevant for us, for the astronomy? Because, as I said before, neutrino pair annihilation has been proposed as a source for gamma ray bursts, but in GR, they don't have the energy to be near to the average emitted energy rate, that is 5 times 10 to the 52 erg/s. And indeed, we have an order of magnitude inferior in GR respect to the respect to the expected energy. While with modified gravity, one can have, as I said before, 2 or 3 times the energy of GR. So we have an energy of the same order of magnitude with respect to that of the expected energy for a GRB. And moreover, with quintessence, one can have even an energy bigger than this characteristic energy. And we use this characteristic energy as a bound for the parameter space of the quintessence, omega Q and C. And in this plot, the orange and red points are excluded for the quintessence using this bound. So in conclusion, we have studied the energy deposition rate in modified theory. We have studied some modified theory that enhance the energy deposition, and we use it to demonstrate that these processes can be a source for GRB, and we use it also as a bound for the parameter space of the quintessence theory, but it can be used also a bound for other theory if the enhancement is very large. And so here I conclude my presentation. Thanks for the attention.
Okay, thank you very much, Leonardo. I just want to say a hello to Peter Hess and Danny Page. They are on air. Okay, so I think now, Martin, we can restart with your presentation again. It's okay? It's okay to you?
Okay, good.
Good. Okay, thank you very much for your patience.
Okay.
So you can start again. Do you need I change your? Okay, okay, okay. You don't need. That's fantastic. So it's okay. I don't need to change our status. Okay.
Okay. So can you hear me now?
Yes, perfect.
Yes,
Perfect.
it's good.
It's perfect now.
Okay, so for the first slides, let me go quickly through them. As I mentioned you before, the context we are is F of R theories of gravity. In particular, we are considering a so-called quadratic model with this parameter alpha. The structure of the star, we have a static aspherical symmetric one, perfect fluid, the structure of the star. We have these constraints upon alpha, and we are moving now for the thermal physics. We have both local and global quantities. The global ones are computed through this integration in tree space. The luminosity and temperature equations, which are here, as you can see, they are basically the same as GR due to the fact that they were derived considering proper mass elements, not the gravitational, the actual mass elements and baryon number densities. So they remain valid here, with the exception that now the metric functions must be computed through a more complex system of differential equations. So the microphysics comes through the equation of state, through the quantities that I mentioned here, the specific heat, the neutrino emissivity, and the thermal conductivity. So important processes that enter into the scenario are the direct Yurka, due to the fact that, as I will show you in some slides, we have a lot of neutrino emissivity from them. This is important because this occurs at very high density, as you can see, and it demands a particular fraction of protons for this to happen. In contrast with the modified one, which do not demand this threshold due to the spectator neutron here. Of course, as you can see, the mechanisms are both fast and slow. The faster is the direct Yurka, which will play an important role, as we will see in some slides. The superfluidity and superconductivity have a large impact over the emissivities and the specific heat. Actually, they enter into the scene due to this gap, and of course, there is several uncertainty due to the formulation of these equations for the gap. So they also come to contribute with another uncertainty for the model. And near the surface of the star, we are going to make this approximation due to the fact that the densities are so low. We will see that this approximation holds valid within this model as well. And this is important due to the atmospheric and envelope part, where we have these light elements between the temperature and the effective temperature relation, which enters through this parameter eta. Now, for the actual computation of the structure, we have these boundary conditions. This scalar curvature enters as an additional degree of freedom, but we constrain it to vanish at infinity. I mean, we are recovering a sort of flat space. The alpha parameter, we are going to introduce this notation. As you can see, we have this A, which is in solar masses units, and this is a multiple of 10. So the maximum deviation that we find is for this alpha 14. We have two concepts. It must be stressed that we have those sort of masses, different masses. One is at the surface of the star, another is at infinity. That is the one we measure. So it is important to notice that there is some difference between them. If we were to measure it at the surface, it would be a lower value than at infinity. So this gives the sensation that we are increasing the actual mass of the star. So as I mentioned it you before, the approximation we are making at the surface of the star is that this expression holds. And this is true. As you can see, the deviation between the expression, I mean, the actual d phi divided by dr of the modified theory, differences makes a difference, a small difference at this value that we adopt at the surface of the star. So we can make this approximation and the code remains the same. The cross thickness we could expect to play an important role on the thermal evolution due to the thermal relaxation time. But as you can see, there is no difference in the mass range that we are studying or that we consider important due to another constraints, for example, from nicer mission. The Durka proper volume, of course, plays an important role, and the additional term in the Lagrangian, as you can see, play a small role on modifying this gravitational mass threshold. So for the actual thermal evolution, we are employing the NS2 code, which is a photon-based one. We are considering at least 3 experiments with simple models, impact of this gravitational surface, and the microphysics. So for the simple models, you can see that the impact of changing this alpha, the most significant effect here is that it lowers the effective temperature of the star. On the right hand side panel, you can see that microphysics have a larger impact. I mean, we have this MS equation of state, and as you can see, the URCA process determines how fast this cooling occurs, in contrast with the gravitational modification. This threshold, as you remember, is density dependent. I mean, locally dependent, not globally. So we have this impact over the equations of state. Now, as you can see, even if we consider a large sample of solar masses, we cannot explain all the objects. I mean, we are still needing superfluidity in order, and as well as light elements in order to try to fit all the available data. But of course, the fact that this effective temperature decreases is due to the local surface gravity. If you fix this parameter, you can see that for a fixed as well solar mass model, I mean 1.4, we arrive to an almost same model. The small differences are due to the different central densities between alphas, but well, this parameter plays the important role in explaining these lower effective temperatures. But now if we include superfluidity as well as the light elements envelope in the game, we can explain most of the data, not all of them, but still it plays a similar role than that of GR. I mean, we can explain several of them, but still microphysics have a larger impact. As you can see, this two solar mass model, which have a direct URCA in its interior, can be make a hotter instead of a fast cooling scenario due to microphysics. I mean, you can modify the gap entering into the scene and not the gravity, and you obtain these results. I mean, you are obtaining explanation for a larger part of the sample than just changing the metric. So for the conclusions, we can see that Schwarzschild metric, as a matter of fact, is recovered at infinity. The labeling of the models is according to the total gravitational mass. That's the impression that we have very massive stars cooling rapidly or slower. The lower GS is responsible for most of these cooling effects, as well as the microphysics. Another notice is that this alpha 14 is in good agreement with the data. So in principle, we could say that this model are still viable if we consider cooling evolution, thermal evolution. A positive aspect is that we can study microphysics without worrying that we have GR or this R plus alpha R squared. A negative aspect is that these killing curves might not be a good candidate to spot differences between models. Of course, the scenario which explains most of the data, all of the data, as a matter of fact, requires another mechanism. And as a open question, we leave this fact that what happens if we consider other models of gravity. So thank you for your attention and this opportunity.
Okay, thank you very much, Martin. Thank you very much. So let's go immediately to the next speaker, Kent Yagi. Kent Yagi, please.
Yes.
Okay. Great. You are sharing already your screen. Fantastic.
Okay.
Very good.
So I guess I should start. Hi, everyone.
Yes, please. Yes, please.
I'm Kent Yagi from University of Virginia, and today I'd like to explain some analytic scalar charge expressions for neutron stars in scalar tensor series that we found recently, and how we can use these scalar charges to constrain these series using especially gravitational waves from black hole neutron star collisions. These works are in collaboration with these people, and they are either current or former students at University of Virginia. And Michael Stepniska will be presenting a follow-up talk later in this session. All right, to get started, I'd like to mention that neutron stars are ideal objects to test gravity. And to give you an example, in this plot, I show the mass and radius of a neutron star, both in GR and in scalar tensor series, with various equilibrium states shown by different colors. The thing to note is that there are some bumps in scalar tensor theory relations, and these are due to spontaneous scalarization that I'm going to explain later. But the point here is that if you can measure mass and radius of two neutron stars independently, then we can probe and distinguish, hopefully, whether GR is correct or scalar tensor theory is correct. So the focus of my talk today is scalar tensor series that admit this kind of scalarization. And the action is given in this form where we have the Einstein-Zorach term, and then there is a kinetic term for the scalar field. Psi m is the matter field, which is coupled to a metric through an effective form where the original G mu nu, the metric, is coupled to some arbitrary function of the scalar field. We can take this arbitrary function to be whatever we want, but Damo and Esposito Fares came up with a very simple example where this A of phi is given by exponential with some quadratic function in scalar field. And there is a coupling constant beta naught. In this theory, there are two parameters, beta naught, and also the asymptotic value of the scalar field at infinity. For convenience, we typically define another quantity called alpha naught, which is given by a product of beta naught and this asymptotic value of the scalar field at infinity. So our three parameters are this alpha naught and beta naught, and they both control the amount of coupling between matter field and the metric. All right, so to explain scalar charges, scalarization, we need to understand what scalar charges are. Well, scalar charges are sources for a scalar field, and there are different ways to compute the scalar charge, but one way is to look at the asymptotic behavior of the scalar field. If you do that, then the leading is just a constant, which is something I've already explained. If you look at the next to leading expansion in 1 over r, then if you look at the coefficient, this coefficient corresponds to the scalar charge. There are two types of scalarization. The first one is what we call perturbative scalarization, where the scalar charge is proportional to one of the coupling constants alpha naught in this theory. On the other hand, there is this interesting phenomena of spontaneous scalarization, where the scalar charges acquire order unity contribution, even if we set this alpha naught to, let's say, 0 or to a tiny number. To give you an idea, this plot shows the scalar charge as a function of compactness. Compactness is the ratio between mass and radius, where I picked alpha naught to be a very small number, 10 to minus 5, and I varied beta naught from minus 4.2 to minus 4.5. Different colors again corresponds to different equational states. Now, if I pick beta naught to be, let's say, minus 4.2, then the amount of scalar charge being induced is roughly of the same order as this alpha naught parameter. Whereas if I decrease this beta naught to minus 4.4, minus 4.5, then all of a sudden, scalar charges can acquire order unity or 0.1-ish contribution. So this part is called spontaneous scalarization. So this bottom regime is perturbative scalarization. The top regime is spontaneous scalarization. Now, all of these are computed numerically for all these dots, and that's because equation states for realistic nuclear matter are given in tables, and we can only solve modified TOV equations numerically. The questions we wanted to address was, can we come up with some analytic expression for scalar charges that will be ready to use? And the answer turned out to be yes. Just to give some reference, there are some analytic estimates done within the context of scalar tensor theories for neutron stars. And for example, this paper studied the analytic estimates for critical beta naught for spontaneous scalarization. In our work, we followed a different paper by Burgess and Holbach, where they make an assumption that this alpha quantity at the center of the star is very small, where alpha at the center is given by a product of this beta naught times the scalar field at the center. And if we make this assumption, then we can expand both alpha naught and also the scalar charge about this alpha c parameter. The leading contribution is just proportional to this alpha c. So what we can do is we can eliminate this alpha c, and what we find is that the scalar charge is proportional to this alpha naught. And this is exactly what I explained for the perturbative scalarization. The situation changes if we include up to next to leading order in alpha naught expansion. Then the next to leading goes like alpha c cubed. And this means even if we set alpha naught to 0, we can still solve for alpha c, and we get this quantity that's given by a combination of the coefficients d1 and d2, which are given here. Now we can plug in this alpha c into the second equation, and we can express scalar charge in terms of E1, D1, D2, all of these coefficients. The point here is that even though we are setting alpha naught to 0, there can be still non-vanishing scalar charge contribution if this quantity inside square root is positive, namely D1 over D2 is negative. So if this condition is satisfied, then there can be a large amount of scalar charge being activated, and this is called spontaneous scalarization. All right. As I said, it's difficult to solve TOV equations numerically. So what can we do? Well, we can take some analytic model, and at least within GR, there is a very useful model called Tolman-7 model, where Tolman assumed that the energy density profile inside a neutron star is given in this simple form in a quadratic function of the radial coordinate. It turns out that this approximation is quite good to compare this analytic estimate against the realistic profile. Here I show the energy density profile for both GR and scalar tensor theories, taking some equation state with some mass of a neutron star, and I compare these realistic profiles against the analytic estimate coming from this Tolman simple quadratic form, which is shown by this black one. And especially at the inner region, like 50% or smaller compared to the radius location, the profile can be described very accurately with this Tolman model. In GR, if we use this simple profile, then we can solve TOV equations analytically. So we get analytic pressure profile or gravitational potential profile and so on. Unfortunately, scalar tensor theories are more complicated. Modified TOV equation is coupled to the scalar field. So we need to solve both TOV and also scalar field equations. And it turned out that it's difficult to find analytic solutions, even if we use this simple model for the energy density. So instead of finding full solution, we tried some approximation and then used some resummation mathematical technique. Namely, we first assume that the compactness of a neutron star is small, and then we expand the field equation about this compactness being small, and then solve that field equation order by order. I skipped the details and just show you the result. The differential equations to be solved will be explained in Michael Stepniska's talk later. For the perturbative scalarization that I explained earlier, where scalar charge is proportional to alpha naught, we can also expand this about compactness being 0. The leading effect is 0th order compactness, then linear order compactness, secondary order compactness, and we can just keep going. In our paper, we derived this expression up to 10th order in compactness, and then we applied Pade resummation to take into account higher order contribution that's being neglected here. Similarly, for the spontaneous scalarization case, to remind you, the scalar charge was given in terms of the coefficients which are shown here. So what we can do is we can try to find analytic expressions for all of these coefficients, then plug that into here. For example, the D1 coefficient can be found analytically in a series of compactness, similar for D2 and E1. Again, we actually derived these expressions up to 10th order in compactness and applied resummation technique. The final expressions are very lengthy, but we have a mathematical script that's publicly available. Here in this talk, I just show you the result where I compare the analytic results against the numerical scalar charges that I've shown you earlier. So these are all numerical values. And then if I show in the same plot, the analytic result shown by either solid or dashed black lines, then you can see that these analytic expressions match quite beautifully with numerical dots, especially with the slide equation state in blue. So this shows that our analytic expression can capture accurately the numerical results. Okay, let me now, oh, and by the way, for Stepniska's talk later, he will be discussing some universal relations involving this scalar charge. So stay tuned for that. Okay, then let me switch my gear a bit and explain how we can use these scalar charges to prove these theories from observations. For example, in GR, if we have 2 point particles moving around each other with relative velocity v, then of course we have a gravitational wave emission, and the luminosity goes like velocity to the 10th power. In scalar tensor theories, we have these scalar charges, and these scalar charges induce scalar radiation. And the luminosity for scalar radiation goes like velocity to the 8th power, and it's proportional to the difference between 2 scalar charges squared. The reason why there's a difference in the velocity dependence between this scalar radiation and gravitational radiation is because gravitational radiation is quadrupolar, while scalar radiation is dipolar. So we can use these estimates, and then we can basically compare this prediction against observations of, say, binary pulsars of gravitational waves. And if we don't find any evidence for scalar type of radiation, then basically we can constrain those theories. Especially now that we have new gravitational wave events with one black hole, one neutron star colliding, it would be interesting to use or study these kind of events. In scalar tensor theories, neutron stars do have scalar charges, whereas black holes do not. Let's see. This plot shows the bounds on alpha node and beta nodes quantum space with binary pulse observations in black and solar system experiments in brown. Anything below to each of these curves is the allowed region. So the current allowed region is somewhere in here. Now, if we made a forecast about 2 years ago that if we have a measurement of gravitational waves coming from one black hole, one neutron star colliding with signal to noise ratio of 10 using advanced LIGO 03 noise curve, and assuming that the neutron star mass is 1.4 solar mass, then we vary the black hole mass going from 5 solar mass to 40 solar mass. And we made a forecast of the upper bound that we should be able to place with such kind of gravitational wave events in this Toronto space. comparing these predictions against the actual event, which I show here, taken by the latest LIGO cooperation paper, especially for this blue event, the SNR was very close to 10. And then the neutron star mass is sort of close to 1.4 solar mass that we assumed. And then the black hole mass was something like 6 solar mass or 7 solar mass. So the constraints should come somewhere around here. And unfortunately, the gravitational wave bound is not as stringent as the existing binary pulsar or solar system bounds. However, we will have a hope of doing better if we go to future detectors. This shows the various future detectors, ground-based detector, noise curve, and also the ones for space-based detectors. The black one shows the gravitational wave spectrum from black hole neutron star collisions. In this talk, I'm just going to focus on 2 example detectors. One Einstein telescope that will be built on ground, one BD-SIGO, which is planned to be launched up in space. Now, if we use Einstein telescope and assume that the black hole neutron star system is situated 1 gigaparsec away from us, then if we just have single event measurement, the upper bound that we should be able to place, in this parameter space is given by this solid cyan curve. On the other hand, we should be able to see multiple events. So we should be able to stack those multiple events. And then depending on how many events we will have, there's a variation, but we should be able to place the upper bound somewhere in this shaded region. The situation becomes even better if we have space-based detectors like BD-SIGO, then the bounds will come somewhere around here. So in terms of constraining alpha node parameter, we can improve the upper bound by a few orders of magnitude. So future gravitational wave observations have quite strong power in terms of constraining these types of theories. Okay, so to conclude, we first derived analytic scalar charges using Tolman 7 model, and then we found very good agreement with numerical results, which provides us a physically motivated way to use analytic expressions for scalar charges of neutron stars. Then we considered how well we can place bounds on these theories using black hole neutron star gravitational wave events. It turned out that with the existing event, it's difficult to go beyond the bounds obtained from binary pulsars or solar system experiments, but with future observations, we should be able to go beyond, and the future is looking good. Okay, that's it. Thank you very much for your attention.
Okay. Okay, thank you very much. Excellent presentation. Very good. So we go now to the next speaker, Benno Boldeman.
Okay. Can you hear me and see my first slide?
Yes, please.
Okay. First, I'd like to thank Cesar Zen Vasconcelos for the possibility to participate in this challenging and interesting topic on the frontiers of physics, where quantum mechanics meets gravitation. The topic of our talk is the branch-cut universe, from origin of the universe to the formation of compact stars. Okay. The standard cosmological model of general relativity, the Friedmann-Lemaitre-Robertson-Walker metric, is a closed set of equations relating the scale factor A of t, the energy density rho of t, and the pressure P of t for a flat, open, and closed universe. If we go back in time, the universe gets progressively hotter, denser, and expands more rapidly. Around 13.7 billion years ago, the density, temperature, and expansion rate of the universe would start off forming infinity, the so-called Big Bang singularity. The predicted consequences of this standard cosmological model are limitations to our understanding of the origin of the cosmos and gravity, implying technically laws of logic, of formal consistency and predictability. The predictions are very far from experimental possibilities. Models allow only speculations about how to prevent singularities. And the big question, is quantization the solution? The analytical lines of the present study is the classical approach. We apply the tools of singular semi-Riemannian geometry to push the limits of general relativity and of time beyond the Big Bang singularity. Quantum approach is the analytically continued version of the renormalizable Wheeler-DeWitt equation. Extrinsic curvature contributions treated in a projectable Horava-Lifshitz gravity model with higher order spatial derivative terms of the curvature of the universe. More details can be found in our references cited here below. So let's come to the motivation. Our motivations are to overcome the general relativity predictions about the presence of the singularity at the origin of the universe and provide an alternative approach to inflation. The applied steps were combination of the multiverse conception of Stephen Hawking and Thomas Hartog of a hypothetical set of multiple universes existing in parallel, the techniques of analytical continuation, and the superposition principle for linear independent systems. The multiverse conception explores confluence points between quantum mechanics and general relativity. The complexification of the Friedmann-Lemaitre-Robertson-Walker metric, which results in a closed set of complex field equations with multiple singularities. Imposition that the multiple singularities of the field equations are confined to the same universe combined with a Riemann sum to approximate the field equation to definite integrals. So we get the following integral equation. Here you see the continuous variable xi of t is an auxiliary function which acts like a shift function and represents a regularization variable. We can define the beta t variable this way, which is shown here in the second equation. And the solution to the first equation is given here below. So we can now start to solve the solution for the radiation dominated era where the pressure is rho divided by 3. I like to mention that rho of t is related to the 4th power of this beta t function in this approach. The solution for the matter-dominated era where the pressure is 0 can be found here. And you see rho of t is related to the 3rd power of the logarithm of the beta t function. So if we compare this approach with the classical approach, we see that these solutions suggest a mapping of the scalar function with the inverse logarithmic beta t function. The inverse logarithmic beta t function represents a complex scale factor of a hypothetical complex Friedmann-Lemaitre-Robertson-Walker metric of maximally symmetric and homogeneous superposed multipole expanding universes existing in parallel. The logarithmic of the beta t also represents a linear scaling factor in time, bringing to time a complex nature with an imaginary component. So how can we visualize these beta t functions? So what you can see here in the picture is the imaginary part of the logarithm of the beta t function, and the right side, the real part of the logarithm of the beta t function. Connected Riemann surface with infinitely many levels extending clockwise or counterclockwise, both upward and downward. Branches of the function are glued along upper and lower half-plane copies. Each 2 copies can be visualized as 2 levels of a continuously spiraling parking garage. And you can go up a level or go down a level and so on, infinitely. Branch cut is the sum of infinitely many poles arranged along a line in the complex plane with infinitesimal residuals. Discontinued jumps of 2pi, going from one parking garage to the next level, up or down this way. So here you see the imaginary part of the reciprocal part of the logarithm beta t function, and on the right the real part of the reciprocal logarithm of the beta t function. Every time the independent variable goes around the branch point, moving continuously to different Riemann sheets, we have a classical mechanism to avoid singularities this way, and this leads to physical implications. The domain brings together the principles of quantum mechanics and gravity of general relativity. So we get, with this approach, these two complex Friedmann's equation, which can be combined to get the analytical continued energy stress conservation law, which is shown here as the equation 10. And of course, we have the complex conjugate of these Friedmann equations, where you can see here the results. As a result, also, we get the analytically continued Hubble rate. In parentheses, you see the modifications where our inverse logarithmic beta functions get into this expression. So how can we interpret this new approach? The branch cut universe divides in two scenarios, which can be analyzed. The first scenario is a we're going on the third picture, you see we're going from left to right, where we start on a negative time, going to the positive part on the right. So the continuous contraction, and we have a systematic increase of the temperature in its negative complex cosmological time sector, and going to the right, we get a continuous expansion and a systematic decrease of the temperature in its positive complex cosmological time sector. The second scenario is the branch cut and branch point disappears after the realization of an imaginary time by means of a big rotation, which breaks the previous connection. You see they are separated now, the branch point, which is replaced here by the real and continuous thermal time, the temperature, and mirrored parallel evolutionary universes adjacent to our is nested in the structure of space-time with its evolutionary process going backward in the cosmological thermal negative time sector. So we can treat these, the inverse logarithmic beta t function, as a quantity which lets us do quantum approach. So we have here somehow a differential equation where u of t is the inverse of the logarithmic beta t function. You see below the sketch of an example for a solution of this equation. Coming from the negative time, we have an oscillating part which gets continuous if we pass through the branch point. Doing this for the negative part, we're coming from a continuous behavior, passing the branch point to an oscillation, to a big oscillation. So using the superposition of quantum mechanics, we can use this to describe the behavior with the quantum approach at the branch point. So please let me do some final remarks. The classical approach, the present formalism presents similarity with quantum bouncing models, QBM, which assume in general a mechanism or trigger to keep the bouncing phase stable, associated with quantum fluctuations. Here the contraction phase amplifies quantum fluctuations and could serve as a trigger for the expansion phase. The classic version of our model does not require mechanisms of this type, as it represents a structural modification of space-time. The quantum approach, we assume a topological quantization of space-time between the contraction and the expansion quantum topological phases due to somehow quantum tunneling or a quantum leap. So the next step is comparison with observations and explaining the homogeneity of background radiation and primordial fluctuations. And now I'd like to take some final remarks about compact stars. The non-singular model with a bounce. In the contraction phase of the specular universe, black holes must form naturally. Unlike the rest of the cosmic fluid that homogenizes in the final phase of contraction, black holes could survive it and then be the cause of the inhomogeneities that give rise to the structure in the expansion phase without the need of to introduce inflation or additional fields. They could also give rise to dark matter, a hypothesis that seems to be in agreement with the LIGO observations. In McVitie models with bounds to study the evolution of dynamic horizons throughout cosmic history, near the bounds, the cosmological horizons and the black hole merge, exposing the singularity, which is weak, not like a big bang. No? In our model, during the expansion phase, the horizon reappears after a while, so the black hole can pass unscathed from one phase to another. But this has to be investigated more in detail. I like to do a special thank to Peter Hess, who has contributed important part to this work, also as Cesar Zem Vasconcelos. Thank you very much.
Okay. Thank you. Thank you, Benno. Thank you. Thank you, Peter. So let's go immediately to the next speaker, Manuel Balheiro. Manuel, estás no ar? Alô, Manuel. Manuel, me escuta?
Oi. Yes,
oi,
yes.
oi.
Okay. It's me already. Yes. Okay, so sorry that I was trying to listen another one in my cellular. Okay. Oh, sorry. Let me shut down this stuff.
Manuel, queres mudar de horário? Quer ir mais tarde?
No, that's fine. But that's fine for me. That's fine for me. It's only that I thought that was late, but later. But that's fine. Let's go. So I will share my talk now.
Okay, please. Okay.
Just 1 minute, please. Where I am.
Share your screen.
Yes. Sorry. Where are you here? Oh shit.
No problem. Take your time.
Yeah. Okay. Now it's okay. Okay. Now it's okay. So share my Okay. Are you seeing now? Yes.
Yes. Please
okay.
go ahead.
Yes. Okay. Thank you. So full screen. Yeah. So my talk is first. Thanks for the invitation, Cesar. Okay, and Aurora, to be part of this important parallel session. This is a work I did together with some colleagues from my institution, the Instituto Tecnológico de Aeronáutica in Brazil, near São Paulo, São José dos Campos. So it's Roberto Lobato and Odilon Lourenço, Pedro Moraes, César Lenzi, all them are from my institution, and also Mariana Dutra and Wayne, and the collaboration from Márcio Avelar from the Astronomy Institute of Geophysics at São Paulo University. This work was published in JCAP end of last year, and you can see here the reference, okay, if you want to have a look, okay. So the main idea, okay, of work, the outline of my talk is here. So I will explain a little bit shortly, of course, the stellar structure in this modified theory, okay, in general relativity, and show the let's say in simple words, show that how important is to use realistic equations of state, okay, and not really polytropics or let's put simple forms, okay, that don't take in account the conditions of, in this particular case, the crust of the neutron stars, okay, this region of low density that many times in the polytropics is not well considered, okay? So let's go. The first idea of in general relativity. First, we are working trying to solve relativistic stars, okay, non-static ones. So you have the spherical symmetry, as you know, the metric of a spherical symmetric object. Also, the perfect fluid of our method inside. Okay, so it's isotropic, okay, as expected. And as you know, we have usually this equation to solve the equilibrium of the configurations. Okay, so here is the mass of the star, or the conservation of the mass, and this is the usual Thoma-Oppenheimer-Volkoff equation, where here you see the contributions from general relativity. This comes from the metric, and these two terms regarding the relation of the pressure, how the pressure is larger comparing to the energy density, okay? It is important to stress that these terms are important even when you have a very small effect on the metric, okay? That is the case of very massive white dwarfs, as I recently with Janssen show, okay? That you cannot neglect general relativity if you are in a very massive case for white dwarfs, even if the metric is not important, because the pressure and the energy become at the same order, and so of course you have a larger gradient, and in this case you have a small radius than you expect by Newtonian theory, okay? But let's go. This work, I will use several equations of state, okay? Of course, I will have no time here to talk about all them, but these are usually non-relativistic equations of state, okay, or scheme ones like this SLY4, okay. You have also some relativistic equation of state, is MPA1, okay, but in this case coming from some Bruckner R3-Fock calculation in a relativistic scheme, okay? As you know, as you see, all them give here radius around 10 to 12, a little bit more than 12, okay? This is some case of an hybrid star, okay, that I will talk later about, okay? So, and here in these colors, okay, yellow and blue, okay, are essentially this event, okay, this GW, oh sorry, this G1708 17, where we saw a merger of two neutron stars, one with masses around 1.2 and another one about 1.6 or 7. So are these two colors, okay? And from them are here the range expected for the radius, okay? As you know, recently, I believe maybe someone already spoke about that because I could not follow all the talks before, okay? But we know now from NICER, this instrument X-ray instrument that is in the International Space Station, that the radius of a 1.4 solar mass and the radius of 2 solar masses, this Demorest pulsar, okay, or neutron star, they are around 12.4 kilometers. So 12 kilometers is more or less what we expected now, or even larger, like 12.4 up to 13, a little bit more than 13 kilometers. So this is creating really a big, let's put a big challenge to all the field now, okay? So, and furthermore, if you see that the mass increases too fast and the radius does not increase, this is only possible if you have a very stiff equation of state. If just after 1 or 2 times nuclear matter density, the equation of state becomes almost causal. That is the solution in Lennard equation when you have the pressure and the energy density almost at the same order, okay, or sound velocity near the light velocity, okay? So as you see, several of these models are not already okay, but of course, everything I'm talking about is about 2 months ago, or even less, okay? So you need to take that in account, but it's really changing our view of the field, okay? This new model, RT, what I'm working now, what I'm going to talk about. So what we have, you have a function that is not only the curvature of Einstein equation, okay, but also a new term like here that connects, the trace of the energy momentum, okay? So you can really do all the Einstein equations now. Let's put the geometric part is the same, but now you have some contribution from the trace of the energy momentum tensor of the matter that will change that equations that I was just talking before, speaking a little bit some minutes ago. So what you have a new contribution for the density and a new contribution here for the pressure, okay? So you can see as some effective density if you multiply by 4 pi here, so 4 pi over 8 pi, okay? So you get essentially a new energy density that is related to this 3 whole minus p new term, and here a new pressure because also this 4 pi PR, you have here R, so you can multiply by 4 pi here and divide by 8 pi, and so you have a new pressure, okay? So this increases the masses and decreases the pressure of the system, okay, an effective pressure in that way, okay? So this is the trace, rho minus 3p of the matter. And also you have this new term. This new term creates some complication. Why? Because this is d rho dp. Rho here is the energy density. So it's the inverse of the sound velocity. So when you go to the crust of a neutron star, where the sound velocity becomes too small, okay, too small, this number gets too large, okay? And in fact, larger than 1. And this means that this lambda needs to be negative in order to maintain this, okay, really positive. If not, if this becomes negative, you change the sign of your pressure gradient, and so your star blows up. So this problem that the sound velocity cannot be, if it is too small at the crust, makes this term too very large, does not allow lambda to be too large. And in that case, if lambda is not too large, the increase of the mass is small, okay? And this is what you have proved, and I'm going to show for you now. We did previous work in JCAP in 2015 with this model, but with polytropic equation of state. Polytropic equation of state sound velocity, okay, is almost constant, okay? So you could have larger values for lambda And in that case, you could find increase of masses. But that result is not realistic, okay? As we already know. Is what we did for these equations of state. This MPA1 is more relativistic, in fact. So you see here is in this pink is lambda equals 0. Lambda equals 0 is GR, okay, general relativity. So you can see in the other equations. So what happens when we increase this, that increase the coupling of this phase distribution of the energy momentum tensor? So what happens in our M over R curve, okay? We increase the radius essentially, okay? We cannot increase the mass. Why? Because lambda needs to be first negative. Here should have a minus sign, maybe you don't see, but needs to be quite small. So what we found, okay, is that when you use realistic equations of state, our previous results that show that the mass would increase, okay, you don't see, you only see increase of radius. And as you see, if you think about this gravitational wave event, okay, you know that after 14 kilometers, okay, you cannot really believe in your star, okay, of mass 1.4. So also this restricts lambda out almost up to minus 0.02, so a small contribution from this modified gravity theory, okay, F of RT. So this is for one equation of state, NP1, okay, this is for another one, okay, that we have used here, okay, and so you see for the others also, you see the effect, of course, more pronounced, okay, for some, from one or others, the increase of this lambda, okay, but you don't see the increase of the mass, okay, so, and you trace back, you know, okay, you have also used some relativistic field models that Cesar knows very well, with a lot of couplings here that make the equation of state stiffer, okay, and we found more or less the same result. In fact, for relativistic mean field theories, already you obtain a radius around 12.5 kilometers. That is what NICER is indicating. So in this case, you cannot even try to have lambda larger than, let's put 0.01, because you already are out of the range.
You can't park there. You can't park there.
At range of the radius, okay? So, so this really tell us that the application of this FRT theory now in neutron stars, okay, and also we apply for white dwarfs, also have more or less the same problem. It's not really good to improve the mass of the neutron stars in order to really get, let's put 2.4 or 2.6 solar masses if they exist, okay? We back this. This is what we have done for this equation of state. Are two of them are non-relativistic, but they are usually used. So here, in my plots above here, okay, these are with crust, okay? So previous result that I just show for you now. So you see no increment of the mass, okay, and only increment of the radius. If you do only that, you take out the crust equation of state, okay, so of course you are not going to have, as you know, this behavior that the curve tends to go to the right, because this is exactly the effect of the crust, okay, I have low density that makes the neutron star curve turning to right, okay. So what you have is essentially this type of curves that are usually seen in quark stars if you don't have any small crust, okay. So see, now if you increase lambda, and in fact at that time our works could go with lambda to 1.2 negative values, okay. So you see that in fact, we increase the mass up to 2.5, 2.2, sorry, 2.2, 2.3, or even a little bit larger. Okay, so is the effect of the crust that make these results not possible. So the results correct are these ones. And even very small effects, if you believe that the neutron star radius of a mass of 1.4 is not larger than, let's put there 14 kilometers, okay? So contribution. So in summary, the objective equations are solved with realistic equations of neutron stars are subject to the joint constraint, massive pulsars, try to produce massive pulsars, but also this event of the gravitational waves that tell us a little bit what we expect for the radius. And what we have concluded is this, as I explained you by the equations. The pressure in the theory depends on the inverse of the sound velocity, the pressure gradient, sorry. So if the S sound velocity is too small, too low in the crust, lambda cannot be larger. So the contribution to increase the mass cannot be, is smaller, it's less than 1%, okay? And of course, you can have an increase of the radius, but not too much if you are restricted to observational values for the radius, okay? And also we realize that, of course, lambda is not very important, so this new coupling of the theory, so you can see that you cannot really see much effects of the densities of states. So they are very different, but the results are not so different. And finally, the crust effect implies really constraints on the theory, and so you need to take that account. And for finally, I think it's important for now, this work, that any study in modified theories of gravity without realistic equation of state for neutron star are not reliable. They cannot be trustable. So we cannot use some form or some, it does not take in account the microphysics of your equation of state, in particular, the crust. Of course, this is a specific case for this theory. In other theories, this effect maybe is not important, but you need to take this in account after now, when we apply equation to modified theories of gravity to study compact stars, neutron stars. That's it, Cesar. Thank you.
Thank you very much, Manuel. Thank you very much. So let's go directly to the next speaker, Rodrigo Teodoro. Can you hear me, Rodrigo?
Yes, I'm here.
Okay. Okay. Okay.
I'm about to share my screen.
Okay, please do that.
This. Like this. Can you see the slides?
Yes,
Yes,
perfect.
perfect.
Okay, great, thank you. So thanks for inviting me to this talk. So my name is Rodrigo Tenorio. I'm a PhD student at the University of the Balearic Islands, and I'm going to present some work developed in collaboration with Dr. David Keitel and Dr. Lithia Sintes on the follow-up of continuous wave candidates from continuous wave searches. So the basics of this is that we are looking for continuous waves, which are long duration quasi-monochromatic gravitational waves, which we haven't detected yet, by the way. And we expect them to be produced by neutron stars presenting some sort of an axisymmetry, such as cross deformations, R modes, or some sort of free precession. And we usually describe these waves by two different sets of parameters, which encode different information. So the first set is the amplitude parameters, sorry, which encode things like the orientation of the source with respect to the detector and the nominal gravitational wave amplitude we would get in a Earth-based detector or any kind of detector. And the phase evolution parameters, which encode information such as the spin frequency of the source, any spin down or spin up effects, and Doppler modulations due due to the Earth motion in the solar system barycenter. Down here, you can see an example of how we would see a continuous wave in the spectrum in detector data. So you can clearly see this yearly Doppler modulation due to the translation of the Earth around the sun. And you can also see the amplitude modulations due to the daily rotation of the Earth and the anisotropic nature of the detectors. So why do we care about this? So the idea is that there's a basic model to explain this kind of waves, which is called the, or so-called the triaxial ellipsoid, which is basically a quadrupolar formation in the crust of the neutron star due to different moment of inertia along the equator of the star. So basically that kind of deformation is usually parameterized in terms of the so-called ellipticity, which is this epsilon over here. And the idea is that by having this deformation and having a body which is rotating, there's a time-varying quadrupolar deformation that ends up emitting continuous wave at twice the rotation frequency of the body at leading over in the multipolar expansion. So as you can see in this expression, the amplitude of this kind of signals for realistic neutron stars is orders of magnitude lower than that of CBC signals. And in particular, if we look at the dependency on the distance, realistic searches are bounded to be focused on the galactic neutron star population. And the other relevant part of this is that there's a dependency on the equation of states of this neutron star population through the ellipticity. So basically, when we do a continuous wave search, what we do is we place constraints of the galactic neutron star population by putting upper limits on the nominal gravitational wave amplitude h of 0, which could depend on the frequency. And then we convert that through some assumed emission model to constrain the ellipticity of this population of neutron stars. So given that, the question now is how should we search for these kind of signals? So a simple example can be seen here. So in the left-hand side, you can see this picture, which is the same spectrum I showed you before, but in this time with a continuous wave signal with a realistic amplitude. And what we do to search in this data is we set up a template bank covering the parameter space of interest, let it be sky positions or frequencies or spin downs. Then we evaluate a statistic using what we call match filtering, which is we model the phase evolution of the signal and then just filter against the data. And we retrieve up layers of further inspection to see what we got from the data. So as you can see here, if we assume that we are looking for continuous waves from a, let's say, a supernova remnant from which we know the sky position, but not the possible frequency because there are no pulsations, we would do a search similar to this one, in which we would be probing different frequencies motivated by some kind of astrophysical prior. And we would find, for example, that if there's a signal at 50 Hertz, we would get those layers up there, which would be the interesting ones. This kind of approach is useful if we have a relatively small parameter space, but whenever we go to blind searches, such as all sky searches for isolated neutron stars or neutron stars in binary systems, the computing cost scales too much, and this is not feasible at all. So in order to overcome this computational challenge, people invented what we call the semi-coherent approach, which is basically that instead of filtering the whole stream of data using a template, we split that data into different segments, filter each data individually, and then combine them all together. That basically correlates the phase evolution from each segment and ends up imposing a looser template on the data, which means things are less restrictive. And the result of that is that, if you see in this picture over here, is that the structures that we see in the parameter space are much wider. And as a result, we end up not needing so much templates in order to catch whatever signal we have over here. So the basic idea is that we would use what we call the hierarchical approach, in which we would use a semi-coherent F statistic to sample this parameter space with a coarse grid. And then whenever we identify this peak, then we would follow up this peak with a longer coherence time, imposing more restrictive frequency evolutions. And this idea is basically the state of the art on continuous wave searches. And that the logic for the follow-up is that once we have a candidate, we cannot ensure that that's going to be a feasible or a true continuous wave signal, in the sense that imposing less restrictive templates ends up letting noise to get into this data. And we would be basically, for example, we could trigger this kind of structures using or looking at detector lines as well. So the relevance to creating a follow-up pipeline is there, and we simply don't know, or there's no standard way of doing it so far. So the latest development on the follow-up of these sort of layers was carried on by Ashton and Briggs in 2018, and they took a Bayesian perspective on this. And the F statistic, which is basically the optimal filter for these kind of signals, it's normally taken as a maximum likelihood estimator, but they thought of it as a base factor, which would update some kind of knowledge or prior knowledge we would have on the frequency evolution parameters. So basically, they would formulate this follow-up as simply a Bayesian inference problem in which we have to sample this posterior probability distribution on the light of the data we just got from the detector. And this kind of adaptive grid search, because that's what basically an MCMC is in this context, was implemented in the pifstat-python package using the TEMC sampler, which was created by Vusen and Farr in this reference over here. So here you can see an example of what we do. If we had the same candidate as before in a frequency around 50 Hertz, and we would like to see in which sky position that candidate is located, we would put several priors on whatever parameters we don't know of, and then just run an MCMC to sample the parameter space until we find the most likely region of likelihood, which we would then continue to analyze. So this is neat in the sense that using an MCMC sampler simplifies everything. We don't have to set any kind of grids, nor we don't have to calibrate anything. We just select a parameter space region, which is small enough, and then just throw an MCMC to it to follow it up. So the overall hierarchical follow-up runs like this. We start with the region, which comes motivated by some kind of high-level search, which uses a certain coherence time to set up this semi-coherent search. And then on that region, we follow up using a longer coherence time to constrain the parameter space region we're analyzing. And then that region is further constrained by continuously increasing this coherence time until we reach what we call the fully coherent follow-up, in which the whole stream of data is used. So you can see example over here. As we increase coherence time, the parameter space gets narrower and narrower. So this is great, but now the question is, what do we do when we reach the final stage of this follow-up? So this is the basic contribution of this work. What we did was to formulate a new statistic using two different signal and noise hypotheses, with which we could evaluate the result of a follow-up and tell whether we are dealing with a signal or we are just dealing with random noise. So we basically need to introduce the noise and the signal hypothesis. For the noise hypothesis, we use the extreme value theory, in the sense that if one had a stream of data of noise and one was analyzing a template, a grid of templates in the parameter space, the resulting statistic from that, in particular, the resulting loudest statistic from that, which would be what we would be following up, would be given by this expression over here, which is simply a maximum over this ensemble of templates. And that maximum on conditions of Gaussian noise, which hold more or less true for real data, would be distributed according to a Gumbel distribution. So our approach is simply to use what we call off-sourcing, which is evaluating this template bank on different regions of the parameter space to generate noise samples, and then fitting Gumbel distribution to that set of noise samples, as you can see here, in order to get an analytical description of the noise hypothesis, well, the probability distribution of given the noise hypothesis. So that's one of the contributions. And then the second one is how we come up with the signal hypothesis. So the basics for this were already worked out by Reinhard Briggs in this technical document over here. And the idea is that if we had a signal in the data, then we would have some, this signal would be quantified by what we call the SNR squared, which I will refer to as SNR. And once we had measured this semi-coherent F statistic, we would be implicitly obtaining an estimate on the signal-to-noise ratio, which then would be propagated to, or we could propagate to estimate what would be the expected fully coherent F statistic. So we measure something semi-coherently, and then we estimate what we would get coherently. And that can be readily expressed using probability theory by simply marginalizing with respect to the SNR parameter. And we end up with this expression over here, which is simple in the sense that these two probability distributions are just chi-square distributions. And this over here can be set to uniform in the case of unknown signals. So this is easily evaluated, can be evaluated very easily. And we can just work it out for whatever candidates we have. In the strong signal regime, which is not the one in which we are right now, but it's useful to get some sense of what's going on. This expression is just a Gaussian distribution, a Gaussian distribution around the maximum 2f given by the candidate, but we will care of it in this slide over here. So if we take those two noise and signal hypotheses and we construct a base factor, we end up with this plot on the right-hand side, which represents the log base factor of what we got, in terms of two new variables, chi sub n and chi s, which represent the discrepancy of the outlier, which is represented with these red lines, with respect to the noise hypothesis and the signal hypothesis. So there are basically three regimes. We have the A regime, in which the outlier is more consistent with the noise hypothesis rather than the signal hypothesis, and basically this base factor is lower than 0 and the signal hypothesis is disfavored. Then we have the second stage, in which the outlier is more consistent with the signal hypothesis than the noise hypothesis, which is this regime of here, in which the log base factor is proportional to the discrepancy with respect to the background. And that's basically that the higher the SNR, the more favored the signal hypothesis ends up being. And then there's a third regime, which is not the usual one. So regime B is basically what we call a detection statistic. But regime C is the one that we see over here, which is that since we got this SNR estimation that can be propagated to estimation on fully coherent things, we have a belt in which we would place the final fully coherent statistic. And hence, if the outlier was beyond that belt, we will be punishing this outlier because that's not a signal, or that's not consistent with what we call a signal, but rather with noise. So after the introduction of this base factor, we used a set of 300 continuous wave signals injected in Gaussian noise data with a duration of 9 months, which should be something consistent with the O2 run of the advanced LIGO detectors at different depth values. So for the non-initiated, this depth value is simply the inverse of the amplitude of the signal with respect to the amplitude of the noise. And we run a set of follow-up stages using this procedure that I just described. And the results are presented in this figure over here. So horizontal axis is the depth. So the farther you go to the right, the weaker the signal is. And the vertical axis is the log base factor. So the higher you go, the more prominent is the signal in the data. And we see this nice dependency of the base factor with the effective depth, which is inversely proportional to SNR. So basically, the stronger the signal, the higher the base factor. So once we set up this base factor and we calibrated it more or less on what we should get on real data, we applied it to a set of outliers found in LIGO O2 data by a set of open data searches. So there are 30 outliers found by 5 searches on open data. So 2 of the searches were using the Falcon pipeline, which is basically a search for continuous waves across the whole sky for unknown sources. Another one is the outliers stemming from the Einstein at home search, pointing at supernova remnants, from which one outlier survived the whole analysis. And then there are 2 searches targeting different kinds of pulsars using the so-called Viterbi searches, which use hidden Markov models to model the frequency evolution, including spin wandering effects. So we selected these outliers, we run this follow-up on them, and the results are shown in these 2 plots over here. The top one is showing how discrepant are these outliers with respect to the noise and signal hypothesis, and the bottom plot is equivalent to them in the sense that each outlier from up here corresponds to one down here, and it's showing the base factor obtained by these outliers. So we put a safe threshold of log base factor equal 90. Sorry, in the sense that it accounts for the shorter effective time of the observing ground due to tone time in the detectors, and also in the sense that these pipelines are within the range of sensitivity of the other searches. So if there was a signal with the sensitivity quoted by the searchers in the data, we should see something beyond 90, and we don't see anything except for these 3 outliers, all of them stemming from the Viterbi pipeline pointing at Hertz sources. So from these outliers, we basically manually analyzed them, and we found that one of them corresponded to a frequency of 20 hertz, which is a known comp in the data of advanced LIGO. Then there was another outlier which was at 26.34 hertz, which is another outlier corresponding to a very strong hardware injection. So this is basically a fake signal that was injected into the detector to test its behavior, and it's so loud that it was producing outliers at different sky positions. And then we found a third outlier at 15.4 hertz, which we manually inspected, and it was consistent with what we would expect from an instrumental artifact, but we could not find the actual artifact origin for this outlier. So having this, then we focused on the next 2 outliers, which were also coming from the Hess-Viterbi pipeline. And these 2 outliers over here also come from one Hertz comp, in this case, one which is offset by half an hertz. So in conclusion, we presented the first complete framework to conduct hierarchical MCMC follow-ups on not layers of continuous wave searches. These results are evaluated using a base factor which we came up with using first principles of probability and extreme value theory. We applied this follow-up on 30 outliers produced by several searches on OpenO2 data. And out of the whole set of outliers, only 3 of them end up above thresholds. We could relate 2 of them to instrumental causes, but the third one, we didn't found the actual instrumental cause. And this new tool will allow for the result of routine use of long coherence time follow-ups on general continuous wave searches. And this will be quite relevant in the sense that we will be able to produce deeper searches and simplify the claim of a robust detection. So that's all I have. Thank you.
Thank you very much. Excellent presentation. And so let's go to the next speaker. Okay. As Nan Jiang. Do you hear me? Yes.
Yeah, I
okay.
can hear you very clearly. Yeah.
Oh, fantastic.
Then you share my screen. Yeah.
Yes, of course. Please do that. Okay, perfect. Perfect.
So can you see it?
Okay.
Yes,
go ahead.
perfect.
Okay, yeah. So maybe I should start it. Okay. Yeah. So hi everyone. My name is Nan Jiang, and I'm from the University of Virginia, the physics department. And today it's my honor to present my recent work with Professor Kantiagi on probing modified gravitational wave propagation through tidal measurements or binary neutron star mergers. So as it's well known, the binary neutron star merger could serve as standard sirens. Since the first detection of binary neutron star merger, GW17817 is a very special event for multi-messenger astronomy, since not only gravitational wave is detected, but also 11 hours after the detection of GW waves, the electromagnetic counterpart, the gamma ray burst, is also found. So people could can get independent measurement of luminosity distance from GW wave signal data analysis, and redshift from locating the host galaxy from the gamma ray burst information. And this combined measurement has many applications. A very significant one is in the field of cosmology, like constraining Hubble constant. Well, in our talk, in my talk today, my focus is on another application, which is to test general relativity, which is the focus of my talk today. So we all know that GR predicts a unique geodesic for both electromagnetic and gravitational wave signals. However, several alternative theories of gravity would predict deviations from the general theory of relativity by having a difference in the speed of propagation between GW and EM signals, as we can see in this propagation equation. And you can see here there is this extra alpha m factor here, which denotes the modified gravity series. So this and this will subsequently gives this modification in the modified luminosity distance inferred from gravitational waves. As we can see here, that if we consider this modification in this wave propagation equation, there will be an extra factor here, which indicates the modification, and this alpha m is present in this interval. so like, and our interest is to like see like how we can measure this difference. So like to work in a more convenient way, we use this theory agnostic parameterization in Annis Balgesam in work in 2018. In their work, they invented this new parameterization to characterize this difference with parameters C naught and N, and and here this Z is the redshift. And as we can see here, this C naught and N has correspondence with alpha M. And also, like if we took C naught to be 1, we can recover the GR solution. And also such a parameterization will allow us to treat this modification in luminosity distance measurement in a very generic way. At the same time, and more importantly, we can map this modified GW propagation parameters C naught and to theoretical constants in non-gravitational series beyond GR. And so like in the 2018 Balgesam et al.'s work, where they invented this parameterization, they also found constraints for C naught and for C naught. And the way they do it is, first they generate a catalog of 1,000 binary neutron star detections for Einstein telescope in this redshift range, and all those events are taken to have electromagnetic counterparts. So the error estimation on the luminosity distance is written in terms of this, and there are two contributions of the error. One is the instrumental error from ET, and another is the lensing effect. And also the other parameters in luminosity distance, like Hubble constant and the parameters concerning the dark energy equational state. It's obtained from the cosmic microwave background and bion acoustic oscillations and supernova datasets, and their calculation is done in Bayesian analysis. And in their work, using this formalism, they find constraints on C naught. So our motivation arises from a concern or problem. So first, rather than being emitted equally in all directions, the radiation from gamma ray burst is beamed into two very narrow cones with opening angles of only a few degrees. So so it means that like only around 2% of those events might point towards us. Then like we would only observe a gamma ray burst if the if the beamed emission was directed towards the Earth, and this means that we are potentially seeing only a very small fraction of the total number of the gamma ray bursts. And if we assume that around 10% of those events have measurable redshift, so this gives in total like 0.2% of the of all the binary neutron star merger events to be detected with a with the electromagnetic counterparts. So this gives a problem. And also we know that the recent GW 190425 hasn't got an electromagnetic counterparts confirmed yet. So, and here, and then gives our, and then this gives us motivation that can we also use binary neutron star events without EM counterparts as standard sirens to test GR. And there are other, there are other attempts to tackle this problem. So like, one is if we combine the galaxy catalogs information with the direction where we receive this this GW signal, and also we can also correlate the neutron star mass distribution information to infer the mass of the neutron stars to infer redshift. But today we are using a different approach, and our approach is through the tidal effect of the binary neutron star events. So we know that the GW waves from binary neutron star systems contain information on tidal deformation, and this is due to the fact that unlike black holes, the neutron stars have shapes and inner structures. So as the two neutron stars are spiraling into each other, they will get tidally deformed by each other's tidal fields. And this very distinct feature has a very good property. It has dependence on the intrinsic mass of the neutron stars. Unlike the post-Newtonian waveforms, as in here, this PM parameter X, which the mass is coupled with frequency. Our tidal correction here has dependence on the intrinsic mass. So this mass and frequency, this mass and redshift degeneracy can be broken if we consider this tidal effect here. And that's how we are going to tackle this problem if we do not know the redshift information from the EM counterpart measurement. So the different things we do here is we use all BNS events within the range discussed in Balgasam's paper, and we employ a merger rate of 10⁻⁶ megaparsec per year, and this makes a total number of 10⁶ events. Unlike the 10,000 events in Balgasam's paper. And here, the major source of the uncertainty is the uncertainty of the redshift, which is this one is accounted for. And since we have a large number of events, we use visual analysis to approximate parameter estimations. Since in our work we use multi-band detections, so we have large enough SNRs. And then we can map this constraint on C0 and N to from the theory agnostic parameterization to the very specific non-GR parameters in specific gravity series. And also, I'd like to talk about this multi-band network we used in this work. So here, here is the noise spectrum density for Einstein telescope and DCIGO, together with the GW spectrum for GW17 or A17. And we can see here that by adding the DCIGO, we can include early in spirals in the analysis, and notice that in the case of this multi-band observations between this detector, there is a range of frequency around 1 to from 1 to 100 hertz, where both interferometers can detect the wave signals. And if you are not very familiar with DCIGO, so DCIGO is the Decihertz Interferometer Gravitational Wave Observatory, and it is a space-based observatory. It's very similar to LISA, but it works at a higher frequency. And here I will present our results. Since we use the tidal effect in this work, so we need to we need to set a fiducial value for the love number, and if we want to set a value for the fiducial value for love number, we need to know the EOS of the neutron star a priori. So in this case, I chose the slide equation of state, and I chose n as 2.5. And here in the x-axis is the fraction of events with EM counterparts. And here this dashed lines corresponds to the 0.02% fraction, as I mentioned earlier. And as we can see, this one is, and this blue solid curve corresponds to the result from the if we use method from Belgasam's method, and if we if we further use multi-band detection, it can get a little bit improvement. And however, if we combine all those events, even events without EM counterparts, we can get a pretty big improvement for Einstein telescope detection, and also for multi-band. And then if we further include multi-band detection, it can give a greater improvement. So as we can see that this improvement of method can increase the detectability of this delta C0 parameter by a factor of few. And also in the end, I'd like to also talk about this mapping example for Brand-Sticky theory. In the Brand-Sticky theory, as we all are very familiar with, the non-GR parameter is also normally this omega here, but in this work, we are concerned with the correction in the luminosity distance. So the non-GR correction is actually this delta phi naught here, and also and also according to this mapping relationship, there is this mapping between C0 and delta phi naught, and if we got constraints on delta C0, we can also simultaneously obtain corrections on delta phi naught. As we can see here, that this improvement is pretty significant as this when alpha equals 0.02%. So as for conclusions, so we use gravitational waves from BNS mergers, both with and without EM counterpart, to probe a modified gravitational wave propagation effect. And this addition of BNS without EM counterpart plus multi-band detection can increase the variability of this non-GR parameter C0 by a factor of 2 to 3. And also, if we look at a very specific example, like in Brand-Sticky theory, this in Brand-Sticky theory, this delta phi naught can be constrained to a level 10 to the minus 2. thank you very much. And that's all I need to talk about my project. Thank you.
Okay, thank you. Thank you very much. Very good.
Let's go to the last
speaker, Mikhail Stepnishka. Please,
Hello,
do you hear me? Ah, yes, of course.
Okay, let me try sharing my screen.
Okay, thank you very much. Please do it. Okay,
Okay.
perfect. Looks perfect.
And can
go
you
ahead,
see my
please.
mouse cursor?
Yes,
Yes.
Okay, good. Well then, hello, my name is Michael Stepnitska, and today I'm going to be talking more about neutron stars and scalar tensor theories. In particular, I'm going to be looking at universal relations and analytic investigations. And this is work that I did with Ken Yagi, who presented earlier in this meeting. So first I want to talk about kind of neutron stars. Neutron stars, they're ideal objects for studying general relativity due to their high compactnesses and high masses. Unfortunately, we have an uncertainty in their equation of state relating their pressure and their energy density. And so that affects kind of how the interior of the neutron star evolves. And that leads to, if we have some certain set of initial conditions for the neutron star and try and work numerically, we can end up with different kind of neutron star configurations, having different masses and different radii. That being said, there are certain relations with different parameters of these neutron stars that are equation of state independent, and these are the so-called universal relations. And here I'm showing a universal relation between the moment of inertia I, the tidal love number lambda, and the quadrupole moment q. And so these are the I love q relations. And what this is showing is that for all of these different colored universal relations, they're all following the same fit line within an error of about 1%. Now, this work is done in a scalar tensor theory. So we're looking at universal relations in modified gravity. And the scalar tensor theory that we're working with, as Kent Yagi explained earlier, is one that was first looked at by De Moor and Esposito Ferese. And what we do here is we have some arbitrary function a of phi, which they chose to be a nice exponential with a quadratic in phi. And as we said earlier, the two parameters that are kind of controlling this theory are the value of beta naught and the value of alpha naught. And so with these higher values of beta naught, we end up with this scalarization, this spontaneous scalarization, which ends up giving us neutron star solutions that are distinct from general relativity. And so in this universal, or in this scalar tensor theory, we look at the I love q relations again. Pani and Berti looked at the I love q relations for a particularly negative value of beta naught. And the more negative values of beta naught, while are being ruled out by various constraints, observational constraints, it's how you end up making theories which are more distinct from general relativity. And so for this particularly negative value of beta naught, we see there is a slight deviation from GR in these I love q relations. And the deviations are on the order of a few percent, which unfortunately is the same kind of error that we had just in our universal relation in GR by itself. The different equation of states all follow the same fit line to within a few percent. And so here we can't really, in this scalar tensor theory of gravity, we cannot really constrain the I love q relations. We can't really distinguish them. But that raises a question, are there any universal relations that are not found in general relativity? And so to do that, we need to start to look at quantities which are not present in GR. And the one which we choose to look at is the scalar charge. And so once again, we look at the asymptotic behavior of this of our scalar field phi, and this 1 over r term, a coefficient out in front of it is proportional to the scalar charge. And What is interesting about the scalar charge is that when we have these results that are deviating substantially from GR, this can be quantified by our scalar charge being order 1. And this is called spontaneous scalarization, even though in a perturbative scalarization case where our scalar charge is proportional to our other theory parameter, alpha naught, is arbitrarily small, here 10 to the minus 5. And that's just saying that the scalar field is vanishing asymptotically. This can also be seen as a phase transition, where the perturbative scalarization, we're back here in GR realm, but as we kind of approach our way to spontaneous scalarization, the GR solution is now an unstable solution, and the favorable solutions actually deviate from GR. And these are where we are spontaneously scalarized. Now, there have been some previous universal relations found with scalar charges. And so this is a universal relation between the scalar charge, a mass quadrupole moment, and the spin parameter, which is related to the angular momentum. And so in particular here, we have a number of equations of states, all with the beta parameter being set to minus 4.5. And we see that they're all following the same sort of surface here. And then in varying the value of beta, we end up varying which kind of surface we're laying on, which universe. So yeah. Similarly, in Einstein ether theory, and this theory is a vector tensor theory of gravity, not a scalar tensor theory of gravity, but there is a quantity analogous to the scalar charge called sensitivity. And this sensitivity quantity ends up having a universal relation when compared to the stellar binding energy normalized by the stellar mass. And the stellar binding energy is the difference between the baryonic mass of the star and the gravitational mass that we measure. And so looking at that difference, we see, and comparing it to the sensitivity, we see that there is a universal relation. And so that motivates us to look whether or not there is what the relationship between the scalar charge and the stellar binding energy is in our scalar tensor theory of gravity. And it turns out that there is a universal relation there. We also set out to provide mathematical support for this universality. And to do that, we needed to come up with an analytic expression for the scalar charges. And so to create an analytic expression for scalar charges, we start with our field equations, which we get just by varying the action with respect to our metric and with respect to the scalar field. And then we make our neutron star assumptions that we're working in a perfect fluid. And here's the kind of axisymmetric metric that we are using, where we are working in a static case scenario. Plugging this back into the field equations, we end up with modified TOV equations. And here we see the modified TOV equations for mass and for pressure. And so what I want to highlight here is in the limit that phi goes to 0, that our scalar field goes to 0, we recover our GR solutions. And so in that limit, in our mass equation, the second term vanishes, and A of phi, which was defined to be an exponential on phi squared, becomes 1 when phi is 0, and so we recover dm dr equals 4 pi r squared times rho, our energy density rho. And similarly for pressure, setting phi to 0, we see these last two terms go away, and this first term, this a to the fourth, just becomes 1, and we once again recover GR. We also have a scalar field equation, and these three equations allow us to kind of tackle our problem. What I've highlighted here in purple is the energy density rho. Right now, every other quantity, every other function has an analytic expression, but we haven't set anything up for our energy density rho. And this is where we use the Tolman-7 equation of state, where we have a simple quadratic expression that has been shown it works very well with GR. And here in this plot, we also plotted our scalar tensor theory to show that the Tolman-7 equation of state is a good approximation and should work for our scalar tensor theory as well. And so when using kind of what Kent Yagi talked about in his presentation, plugging it into our differential equations, we end up with scalar charge as a function of compactness. And we see here, once again, that scalar charge as the function of compactness, our analytic solutions very nicely model the Sly equation of state. And as a comparison, I show constant density solutions. So instead of using the Tolman-7 equation of state, we use a constant density equation of state, and these are significantly translated from where the numerical results are lying. Now, when we started, we wanted to find our scalar charge as a function of binding energy. And so it turns out that binding energy is important in some supernova scenarios, in particular the electron capture supernova. And binding energy has a very nice relationship with compactness. And so here we see Tolman-7 in our, or so this is all in our static neutron star assumption. We see that binding energy is linear in compactness with a correction of order alpha naught squared. And remember, we were taking alpha naught to be 10 to the minus 5. And so these are vanishingly small. So we work with just linear approximations for both Tolman-7 and constant density. Now, when applying these translations to the data, we end up with a nice looking, or we end up with an analytic expression for the scalar charge in terms of stellar compactness now. And when looking at this, we certainly see a quasi-universal relation where all of these equations of state are lining up right along our analytic solutions. And this is happening for beta being minus 4.2 and minus 4.3. For minus 4.4 and minus 4.5, these negative values of beta are where spontaneous scalarization occurs. And in these scenarios, it actually turns out that we have a multi-valued nature to our function, which is not captured by our analytic expressions. But for this perturbative scalarization case, we are able to capture everything. Now, I also plot the constant density solutions to show, actually, first let me make sure to highlight this red region. So this is where we were having our scalar charges as a function of binding energy. And to leading order, to first order, these expressions are exactly the same. We only see differences in the second order expressions, which is further just supporting this idea of universality. Moreover, we remember that when comparing to compactness, this constant density solution was not modeling the data well at all, but now it is. And it turns out that this is all within 10 to the minus 3 accuracy, so about 0.1% for this region. So now I want to talk a little bit about future work that we are doing. Instead of working on the scalar tensor theory, which I've already described, we add in a potential term to the scalar field. And this is called a massive scalar tensor theory of gravity because the potential that we are choosing here, it has a mass, a scalar mass associated with it. And it turns out that when we look at the modified field equations, the modified TOV equations, the asymptotic behavior of our scalar field goes like a Yukawa potential. We have e to the minus m phi r over r. And there is another solution to the equation, e to the plus m phi r over r, but this is not a physical solution because as we let r go to infinity, we would see the scalar charge is also tending towards infinity as long as we're letting the scalar mass be positive. And we are working in cases where we want the scalar charge to vanish asymptotically, and so that doesn't help us. That being said, the fact that this is a solution mathematically means that when modeling these neutron stars numerically, it makes it hard to just integrate out directly, because when integrating numerically, sometimes the differential equation solvers will pick up on some of this positive mode, which we are not interested in, but this positive mode just blows the solution into nothingness and it is not working. So what we need to end up doing is using a shooting method where we alter values at infinity, where we alter values at the center of the star, and we shoot them to the radius of the star. And at the radius of the star, applying continuity of the scalar field and its derivative, we're able to get notable values back. And what's shown here is the IQ relation between, well, yeah, just the IQ relation in the scalar tensor theory. And what's notable is that the percent difference, it is on order 10%, 20% difference than GR. And that is notable because without this potential term, we could not distinguish the theory from general relativity. So in conclusion, we derived analytic scalar charges with the Tolman-7 equation of state and found a universal relation between scalar charges and the binding energy. This was supported mathematically, and yeah, we have physically motivated, ready-to-use analytic expressions for scalar charges. Thank you.
Hello. Great, fantastic. So we can start now our discussions, okay? And I would like to open to everyone that wishes to make any question to any of the speakers, please just make a signal to me in order I can start to organize this discussion. So please be free to make your questions, your comments, anything you wish.
César, como tu faz o Chico? Sim.
Any question? Please. So, bota ali como co-host.
Eu não sei como fazer.
Ali em cima. Aqui.
Aqui?
É. Mais.
É no more?
Mais. Eu caí mesmo.
Pô, não tem não.
Eu vou ter que sentar aí então. Porque eu não consigo.
Você acha que continua assim, César? Eu estou te ouvindo.
Ok.
Tá tudo bem assim, eu acho.
Ok. Ok. Eu tudo deveria ter deixado.
Não vão ter questões?
Questions? No questions? Recebesse minha mensagem aí do chat?
Sim, não, tem nada aqui.
No questions. Oh, since we have no questions, I think we have to close the section, okay? So thank you to everybody for your participation. So amazing contributions, amazing talks, and I think we should great talks. really great talks. Fabian Wittens wrote great talks, speakers, yes, really great. Maybe Fabian has a question, no?
Temos 15 participantes.
Yes. Aurora, do you have any question? Do you hear me, Aurora?
O microfone dela está desligado.
Yeah. Well, Danny Page, congratulations to everybody. Thanks, Danny. Thank you very much. Well, it seems that we have to close this section. Thank you again to everybody for all amazing talks, and hope to see you as soon as possible. Bye-bye. Bye-bye to you all.
Bye-bye.
Bye-bye.
Bye-bye to everybody.
Bye-bye. Bye-bye.
Bye.
Thank you.
Bye-bye.
Thank you very much.
Thank you very much.
Thank you. See you.
See you. Bye.
Bye-bye.
See you, everybody. Bye.
Danny, good to see you.
Bye, Cesar. Thank you for
Thank you
the
very much.
Yeah.
Okay, thank you very much. Okay. Bye-bye. Bye-bye to you all. Aurora, hasta la próxima vez. Manuel, que bom
Oi,
te ver.
César, tudo bem? Eu não pude participar dessa parte final aqui, porque eu estava aqui numa outra, tem uma aluna falando numa outra sessão, né?
Não, mas
Então,
tudo bem, isso acontece.
Mas
Acontece.
foi ótimo, correu tudo bem, né?
Tudo ótimo, tudo excelente.
Perfeito. Um
É isso
abraço,
aí.
tá? Tchau.
Abração.
Tchau.
Tchau. Aurora! Aurorita! Mira! Cá. Não tem um rum de Cuba aqui?
Ah, o de Cuba.
Ah, tem?
Cuidado,
Não.
César.
Sim.
A coisa estava
Não.
quase.
Temos rum de Cuba, cara. Ok, bye. Bye.
Sim, ok.
Ok? Eu acho que a gente pode, então, desativar, né?
Acho que sim, né?
É.
Eu vou aqui.
Como é que nós fazemos agora para encerrar a sessão?
É só sair, César, eu acho.
Vai ter que sair para todo mundo, né? Ok.
Vou sair do meeting agora, né? E aqui, o que tem que fazer aqui?
Pois é.
Só fechar, né?
Eu acho.
Uhum.
Acho que sim, né?
É.
Ok?
Perfeito.
Foi bom no fim, né? Uhum.
Nossa, como é que ficava agora o resto do meeting? Nós temos
Como é que eu
acesso ou não,
termino?
Cisa?
Eu não sei.
Caso esse senha, né? Eles
É.
mandam